So let me first spend about 5 minutes on what we did in the last lecture. We considered the zeta function of Hurwitz, which we defined by this series. And then we have shown several different representations. The first one was the one in terms of the Riemann zeta function. Which we used to discuss that the zeta function of Hurwitz has only one singularity at s equals 0. Then we used the Mellin transform to show that this is an alternative representation. And we used this representation together with the Bernoulli polynomials to find the values of zeta at negative k. And towards the end, I mentioned that the disadvantage of these representations, of this one at least, is that it's only valid in the half plane, and it would be very nice to have a representation that is valid just everywhere. And we started to look at these contour representations for the gamma function at the end of last class. And the first result today is going to be the analogous representation for the Hurwitz function in terms of a contour integral. And this representation reads as follows. And I'm not going to do the full calculation. It's very similar to the one that we did last time. So let me only provide the idea. Remember the contour, which is also called the Hankel contour, looked like this. It's anti-clockwise. And just looking at the integral, you discussed as the last time that when you send the radius of this circle to 0, there is no contribution. You only have to worry about those two parts when you choose S to be large enough, the real part of S large enough. Even we have a branch cut of minus t on the positive axis, you pick up these different phases which combine to a sine. So doing exactly the steps that we did the last time, this is the way you get the sine piece. And you get the integral along the real line. Which reproduces, apart from the factor gamma, the definition of the Hurwitz zeta function. Which is the assertion that I have stated there. Right. You have to stay away from the singular points of 1 over psi. Okay. But as said, the nice thing about this is that it's a representation for all values of S. Now, why is that representation nicer for certain respects? Well, let's look how to evaluate the properties at the points S equals negative k. I mean, we just said that this representation is not valid at these points. So a remark about the understanding. The sign of S vanishes at the points S in Z. Gamma at S has a singularity at the negative case at least. So let's concentrate on the negative case for now. So we have a 0 multiplying a singularity, and the product will give a finite value. And I'm going to evaluate the integral for S in Z, which will multiply some finite number coming from here. So let's concentrate on the evaluation of the integral for those values of S, and that will give the values of the Horwitz function at negative k easier than the previous calculations did. So how does that work? The important observation is if S is an integer, we get powers or inverse powers in T. So we do not have a branch cut anymore. Yeah, this is a nicely defined function. And in that case, the two contributions from the upper path and the lower path, given they go in opposite directions, they simply kill each other. There's now no branch cut in between. We can take them to be the real axis, and those contributions simply eliminate each other. And for S in Z, the only thing that remains is the little circle. Now, if you look at the integrand, the circle for this representation to be valid must have a radius smaller than 2 pi. Otherwise, we are including a singularity from the point t is plus or minus 2 pi I. So here you should have in mind that what we had a radius epsilon here yesterday, this epsilon has to be smaller than 2 pi for this to be valid. Then the only singularity that is inside the contour is located at t equals 0. And the integral can be evaluated using the residue theorem by simply looking at the coefficient of the 1 over t term in the expansion of this expression. And that expansion is exactly identical pretty much to the definition of the Bernoulli polynomials. So let's say here, so in order to apply the residue theorem as mentioned, we want to look at the Laurent series of the integrand about the singularity, which is t equals 0. And rewriting the integrand again in the fashion that the definition of the Bernoulli polynomials shows up that was the way we wrote this. Yeah, so this is exactly the integrand. And using the definition of the Bernoulli polynomials, this represents the series expansion about t equals 0. Yeah, so this is exactly the generating function for the Bernoulli polynomials, meaning this equals that. So how would you use that to evaluate the integral at those values? Let's just look at s equals 1 to reproduce the residue. If you put s equals 1, then here we got a 1 over t term. We want the residue, so we want the coefficient of the 1 over t term. The coefficient of the 1 over t term for s equals 1 follows from n equals 0. And so we see that if you put s equals 1, then there is a minus 1 over t plus other powers in t actually there's a plus 1 over t minus 1 over t. And we don't care about the other powers for the application of the residue theorem. So the integral at s equals 1 equals 1. If you multiply, if you look at the limit as s tends to 1 of this expression, then you get minus 1, or you get minus pi, and putting things together, you will see that the residue of the Hurwitz function is 1. You can do exactly the same calculation for the other values of k. I'm not going to do that explicitly. But if s is negative k, in order to look at the 1 over t piece, you then have to choose n equals s plus 1. Sorry, n equals negative s plus 1. That will give the 1 over t power. And you see that this gets the Bernoulli polynomials with index k plus 1 involved, as we have found before. So evaluation of particular values reduces to the evaluation of a coefficient in a series expansion, which is much easier than what we've done the last time. And this concludes the Hurwitz zeta function. So we are now going to look at different other zeta functions. And yesterday I was asked, well, why do we look at these zeta functions? And these questions will be answered. I mean, several of Lloyd's lectures and of my lectures will be about why one considers these kinds of zeta functions in physical contexts. So this lecture will be mathematical, but the following two lectures will show why one considers these different zeta functions. So the next one I want to consider is the Barnes zeta function, who was introduced in 1903. And that is a generalization of the Hurwitz zeta function, and instead of just having one sum, you have a multiple sum. I'll explain the notation in a second. If there's too much notation around, take all the R1s through RD to be 1, then it looks already a little nicer. But the main difference, as you see, to the previous case is that we have D summations instead of just 1. I want this argument to be positive. So let's assume C is a positive number. All the components of R are positive numbers, so that this complex power is defined. This is the restriction on the convergence. I mean, for the Horvitz zeta function, it was larger than 1. Now we got D summations, and one can show that this is the needed restriction to impose. You can use, for example, the integral test to show that this is necessary. Now again, not to be overwhelmed by notation, let's look at an example where we take 2 summations. So let's put D equals 2, and let's take all the R's to be 1. So this notation means we are looking at the vector 1, 1. All components are 1. It's actually not a unit vector in 2 dimensions, but it has components 1, 1. So this is the function we are looking at, and we want to know some properties of it. And again, one strategy is to rewrite it in terms of something that we know. In the meantime, we know the Horvitz zeta function, so let's try to rewrite this expression using the Horvitz zeta function. And the observation is, well, that maybe we can resum this somehow and make more sense out of it. Because if M1 and M2 are integers, then certainly the sum will be integers. They both run over N0, 2, so their sum will run from 0 to infinity. And you can make a substitution where you say your new variable is the sum of M1 and M2. If you look at the summation lattice, if you want to call it that way, then if you sum first over M1, you are essentially summing horizontal lines. So if you have absolute convergence, that would be one choice. If you sum first over M2, then you would be summing vertical lines. In this situation, the suitable resummation that allows you to really see something is if you sum the off diagonals. And what is the property of the off diagonals? You see that the sum of M1 and M2 is constant along those lines. So if you let K be the sum of M1 and M2, then the sum runs from 0 to infinity, and you have to count the number of possibilities to write K as a sum of M1 and M2. And there are K plus 1 possibilities to do so, because M1 and M2 run between 0 and K, and there are K plus 1 possibilities to write the integer K as a sum of 2 integers running between 0 and K. And now you see where that allows us to rewrite Barnes in terms of Horvitz. So we get zeta Hurwitz with argument s minus 1 from here. And with argument s from the second term. So that is an explicit representation of this two-dimensional Barnes zeta function in terms of Hurwitz. We also see explicitly that for s equals 2, we have a singularity, as we have expected from the convergence criteria of these multiple sums. Now, this can actually be done in any dimension. So let's briefly look at this. Oops, I want all the r's to be 1 for now. And you can make the similar consideration as I did here for the two summations. So you introduce k to be the sum over m1 through md. The range is therefore 0 to infinity. And we have to multiply this by the number of possibilities to write k as a sum over d integers. And in case you haven't seen that nice way of evaluating this number of possibilities to write k as a sum over the integers, let me briefly provide some nice way of doing it. So you look at the geometric series 1 over 1 minus x to the power d. For each vector, you use the geometric series. Then as we did up here, for the sum over L1 through LD, we introduce the new index k. And the coefficient of the power x to the k will be the number of possibilities as before to write k as a sum over d integers between 0 and k. So that's one way of doing the calculation to see that this number of possibilities get involved. On the other side, you can simply use the binomial formula here. Write down this answer. And by comparing, you see that this combination is the number of possibilities to write k as a sum over d integers. Now, without doing that explicitly, if you substitute that up here, in a slightly more explicit form, using the property of the gamma function, that gamma at z is z minus 1 factorial for z positive integer. If you write this number out for particular values of d and proceed as the first line, some manipulation, you can rewrite this multidimensional sum again in terms of a linear combination of Hurwitz. So I'm not going to do that again, but this leads to a linear combination of Hurwitz. So everything is made very explicit, and we can avoid multidimensional sums when all Ri's are equal to 1. Any question about that case? Now, something similar can be done if the R's are rational, but nothing similar can be done if the R's are real. And if the R's are real, then we need to continue along these lines here. So the representation that corresponds to this line is the following. I erased the definition, too bad. I guess I write it down again, maybe here in the corner. Oh, here it is. Yeah, you see the only difference to Hurwitz is if you use the Mellin-Barnes representation, you get an exponential minus t, not just c plus n, but this is the exponential that you get within the integral of the gamma function. Yeah?
You said that something similar can be done.
Rational, like 5/3 or. It's by no means straightforward. The only thing I'm saying is it can be represented in Hurwitz zeta functions again. But it's a much lengthier process and by no means as simple as this one. So you have to write numbers in terms of mod things, and it's really a little messier. And I can give you a reference if you want to see the details. Mm-hmm. Say that again, sorry. I'm not sure they don't have any, but it hasn't been used in any sense. So continuing here, and in a sense providing the proof, just as a side remark. Yeah, remember yesterday we wrote down the formula that follows from the definition of the gamma function. And that was valid for all positive lambdas. And this is what we apply now to the Barnes, where lambda is this combination here. And you know the nice property of the exponential. So we keep the e to the minus tc, and the rest, I mean the other factors. So this is e to the minus tc, e to the minus t m1 times e to the minus t md. So we can factorize all these, I mean this sum into a product of exponentials, and then summing over m1 up to summing over md can be done explicitly by the use of the geometric formula again. So the multidimensional sum reproduces of two one-dimensional sums, which are geometric series. I forgot those, so there are the R's. For the general case, thank you, there are the R's. Fortunately, the argument remains true. It's still a one-dimensional geometric series, which you can perform, and you can get this integral representation. Yeah, it's really following exactly as here. And using the procedure we used here, again, really identical calculation. Yeah, again, this is the calculation we have done here. You just do exactly the same for this case. Nothing too exciting going on. That's the reason I don't write anything. But done. And you can use this as the starting point to evaluate residues and particular values. And I'm not going to do it. I will give you a sheet of paper asking questions and stating the results. But the strategy is exactly as before. Here we used Bernoulli polynomials. Now there are generalized Bernoulli polynomials, which have been introduced not by generalized Bernoulli, but by Norlund. So let me just mention this definition. And the definition is motivated by this factor. So the generalized Bernoulli polynomials is you take this integrand as the left-hand side, And there are a few factors around by convention. I may get them right, but I supposedly better check. It's a lot of notation around, which is a little bit annoying, but can't be helped. So I guess that is something I really should look at, because if you want to reproduce the residues and the special values, that is going to be the definition to be used. Yep. And looking as we did for Horwitz at integer values of s, there's no branch cut. The only thing that contributes is the little circle. So the values of the integral for integer s are determined by a coefficient in this Laurent series. And you have to fiddle around a little bit. But what you see is we want the 1 over t term to pick up the residue. So we want a particular summation index. The power that we have is t to the s minus 1 plus n minus d. Which shows that the relevant summation index that we will need is d minus s. So when s is an integer, the contributions are coming from this particular summation index. You collect all these factors, and you'll get residues and function values for the Barnes zeta function. Yeah, and that is what I plan to say about this one. Any question about Barnes? His hobby, in a way, was mathematics. He actually was a bishop of Birmingham. So that was possible at the time to be a distinguished theologian and a distinguished researcher. Then final example, Epstein, again 1903. 1903 apparently was the year of the zetas. And there we now look at a quadratic instead of a linear combination of integers. That makes things harder in a certain sense, but at the end, not really. So let me define what that one is. This will be the relevant one to discuss Casimir energies and to discuss cosmological applications, as Floyd will show. Same understanding as before. All these numbers should be positive. So as mentioned, instead of having a linear combination, we now look at quadratics. And I chose to sum over all integers. There are different examples where you want to sum only from 0 to infinity instead of negative infinity to plus infinity. That changes some details, but not the general ideas. So the fact that we have squares gives the d half here. Yeah. For large m's, where the numbers are getting bigger, so the quotient is getting smaller, that improves the convergence behavior. And again, you can use the integral test to show the region of convergence is given by this half plane. Now, if we try the analog of this representation here, we can get an analog, but it's not as nice as it has been. For reasons that are apparent once you start doing this calculation. Yeah, using the arguments used previously, if you interchange summation and integration, and use again this Mellin transformation trick, then this is the identity that you get. Sorry?
Are we allowing the mi's to be 0?
Yes, sorry, I'm running. Oh, that's a mixing of notations. I don't want the 0 here.
Okay, that's
So I'm really summing from negative infinity to plus infinity, including 0, which is possible as long as c is positive. Once you have an example where c is 0, you want to exclude m equals 0. Sorry?
We're only excluding the origin.
We are not excluding anything here. We're summing from negative to plus infinity for all integers mi.
Over there, we just exclude the origin.
No, I just erased it. So I'm still summing over all. And you see the difference between this example and the previous ones is we now have to deal with a summation e to the negative t m squared instead of just m. And there's no geometric formula for that case. So we have to come up with something different in order to proceed from there. Again, done. I like those proofs best. So what can we do in order to go ahead there? Well, this has been provided by Floyd in the first lecture. It looks very different from what he was saying, but it is actually exactly the same. We are now using the Jacobi identity in order to proceed. So I write down the Jacobi identity in explicit terms. Well, yesterday, that was the way it read. And I'm basically writing this out in terms of series to apply it to the case at hand. And again, to get the factors right, this is what the Jacobi identity looks like. But I simply state Floyd lectures. This was not the first time it was proven, but it's the Jacobi identity as mentioned, so the proof goes back to Jacobi, of course. Now let me stress what is relevant about this also called resummation formula for the given context. Now, as we have seen for Horwitz and Barnes, the poles and the special values were determined by the small t behavior of the integrand. Because the large t behavior doesn't contribute any singularities, because we have an exponentially damped contribution. So the main terms for our considerations came from the small t behavior. Now, if you look at the way this is given, the small t behavior cannot be read off. You know that at t equals 0, where this obviously is divergent, but you cannot read off how it diverges. It's just an enormous sum of terms that are getting very, very small for large values of m, but it's impossible to read off this small t behavior from here. The only thing you know, as said, is as t tends to 0, it definitely diverges, because you're summing infinitely many points here. And that's exactly the advantage of this resummation. It shows you explicitly the t to 0 behavior, very explicitly. You have 1 over t here, so whenever L is different from 0, this is exponentially damped. It's exponentially small as t tends to 0, as soon as L is different from 0. Only for L equals 0, well, this is 1, and you see the behavior as t tends to 0 is a 1 over square root of t term plus terms that are exponentially damped and come from the summation over L with L different from 0. So if we write that here, just symbolically, L equals 0 gives this contribution, because we have e to the 0, and then the other L terms give exponentially damped contributions. Okay? And given in the previous examples, the small t behavior gave the relevant contributions, it's a kind of intuitive that this should be the relevant term to consider further, and I'll make a few remarks about those terms afterwards. So let's just consider contributions from the summation term 0. Sure.
R in that, is that just the vector?
Correct. The reason I wrote it exactly in this fashion, and I should have said it why I wrote it in this fashion, is this has exactly the structure of each of these terms. So when we apply it, we will choose R to be R1, R2, R3, up to Rd. Because again, this exponential can be written as e to the minus tc times factors, d factors, each factor having an e to the minus t ri mi squared. And we are going to apply this formula to each of the factors. There are 10 minutes left, so supposedly 2 boards should be enough. So as mentioned, I want to look at the contribution coming from L equals 0, which up here will mean m equals 0. Only then I have a polynomial behavior in T and not an exponentially damped behavior. So again, I apply this formula to each factor e to the minus t ri mi squared. What is the resulting contribution? If m equals 0 is considered only, let me make this the notation. So just m equals 0 is considered. I still have the factor e to the minus tc, because I leave that unchanged. And I resum each of the factors and take the corresponding index mi equals 0. So only, what I have is, for now, just that factor, and I have it d times. Yeah, so it's this factor over here with r replaced by ri. And I applied 2 I equals 1 through d. And I've neglected all other summation index at this point. So that is what the contribution looks like. And that combines to something we've seen before. This is essentially, again, the gamma function at s minus d half with some factor involving d, which follows from the representation I might have erased, the one from last class. Yep, bye-bye. And that allows you to write down the contribution in this form. There's a gamma at s minus d half, and there is a c to the power s minus d half. If you look up the formula for 1 over lambda to the s as an integral, that is what you get. So that is the contribution from m equals 0 only, and we would expect from the previous considerations of Horwitz and Barnes that this determines all the poles and most likely also the particular values. If you look at it, where are the poles? Gamma at 0 has a singularity which corresponds to s equals d half. So the rightmost singular point is at d half, which again is expected because whenever you hit the limit of your convergence region where you expect the pole sitting somewhere. And then the singularities are furthermore if you go down by 1, you see for the, well, not for the first time, but we have now several singularities. If d is even, Let's take 6 to not get confused. Then there's a pole at 3, at 2, and at 1. This is singular at 0 also, but when s equals 0, the singularity is cancelled by the 0 of 1 over gamma. So there's no singularity at 0. -1, and so on, you have the same argument. For d even, those are all the singularities. For d odd, it's a little different, because now the odd ones do not hit the zeros over here. So if d is, let's say, 3, s equals 3/2 gives a singularity, s equals 1/2 gives a singularity, s equals -1/2 will lead to -2 in that case, and that is not cancelled by a singularity here. So for odd dimensions, there are, for the first time now, infinitely many singularities. And that's what you actually have to expect in general. So the singularity structure of those functions can depend heavily on the dimension. So that is the remark about the contribution from m equals 0. Well, now there are all the other ones, and I'm kind of hesitant to talk much about them. They lead to what is called a Bessel function. So one is lucky in the sense that you can actually represent it in terms of known special functions, which makes everything numerically at least very easy to evaluate. You can type it into Mathematica. Bessel K is the name, not a big surprise. And you can produce explicit values if you have to. And that's what is needed in physics. So let me write down the definition of the Bessel function to give you an idea how it shows up. And then I will write one more line, and that will be it. So what is the definition of the Bessel function? Is often referred to as Kelvin function. Yeah, so just take that as a definition of a nice special function. I mean, they are relevant in the context of differential equations for spherically symmetric situations. It's a kind of a standard solution that, well, just describes the solutions there. That's the reason why it actually got a name and is a special function. Why do we need the condition? Well, you see, we want z squared to have a positive real part so that as t tends to 0, this is actually exponentially damped, and that will make the integral well behaved. Yeah, it might have a polynomial singularity at t equals to 0, but that will be killed by exponentially damped behavior. So altogether, it's well behaved.
So that condition is
Right, correct. And as t tends to infinity, everything is fine because we have an exponential damped factor here. That goes to 0, and an additional polynomial decrease or increase doesn't matter. Exponentially damped will kill it. So that's well defined under the given assumptions. Why is that relevant? Well, if you look at the resummed form, you have the factor e to the minus tc, which corresponds to this one here. Once you substitute Tc for T. And the 1 over T contribution comes from here. When L is different from 0, there will always be a 1 over T factor. And you see this matches exactly the definition of the Bessel function, where z squared contains the Ri, it contains the L squared, and the pi, and so on. So one can figure out what the exact factor is, but you see that formally the Kelvin function shows up for each single index L. And so, last line, the way the Epstein zeta function can be represented is this here. Let me make that the star of today. So it's the contribution from m equals 0 plus a series over Kelvin function. And for practical purposes, this is a good representation, because actually it's a d-dimensional sum over infinitely many points, but what is mostly needed is just a kind of 10 indices in this summation that will give all the information that one needs. And in the few sheets of paper that you're going to get, those representations then can be used to find the residue and to find particular values. And that will be used for Casimir energy, as mentioned, and for cosmological applications. And I think the pieces of paper should be ready now, and you will get them the latest tomorrow morning or this afternoon. So thank you for your attention.